All right, so last time, quick refresher, right? We were covering linear models. That's kind of our starting point. And then, like I mentioned before, we're going to build off of that, eventually getting to more non-linear territory. So last time we talked about how we estimate linear models, right? Specifically our coefficients and then our standard errors, and then importantly interpreting those coefficients and standard errors. So today we are going to think about different metrics for evaluating basically how good our model is. So we talked last time again about some of the things that we can think about when interpreting the model. So that includes, the coefficient, standard errors, and the statistical significance thing, right? We did, again, I want to reinforce that that is like one part of a model that has a particular meaning, but we don't want to kind of over-interpret the importance of that. We talked about the R squared, and so what other things are we going to think about today for measuring kind of the quality of a model? So the first one that I want to point us to, and this would help actually a lot specifically with examples like the one that I showed at the end of class last time, the Anscombe quartet, right? If you guys remember, we had those 4 plots that from a perspective of coefficients, statistical significance, and R squared all looked very similar, right? But then the actual distribution of the data and whether or not it makes sense to apply a linear model to it maybe looked a little bit different. And so, how can we go about looking at something like that? So the first one we're going to start off with today is residuals. Okay, so a residual is, residuals, so this is the deviation between observed value and estimated value, or our predicted values. Okay, and so this is actually something that we've been touching on throughout the course so far. So let me just give a quick refresher, and I'm going to try and actually show, well, okay, let me do this part first. So we're going to have a little plot like this. We have our x-axis, we have our y-axis, and then we have some points. All right, let me see if I can replicate my notes over here. Maybe we have something like this. Okay, and if I draw kind of like a best fit line, kind of like this, right, we have already seen this idea of thinking about the error or the distance from each of these point estimates to our predicted line, right? I call that an error. This is essentially what a residual is. It's the same thing. Okay, and so what I'm actually going to do here is I'm going to plot the residuals in a specific way. So here, let's say this is at y equals A, at y equals B, and at y equals C. So let's say this distance is, let's say this distance is 1. Let's say this distance is 2. Let's say this is, or -2. We'll call this one -3 away from it. Maybe this one is 2.5, and this thing is 2 away. Okay, so I'm just kind of roughly eyeballing it here. So we can actually plot something that looks like this. So we can have our residuals here, and we would have our predicted y over here. Okay, and so there is a corresponding y with which these points all line up. And so if I have something like A, B, C, and let's suppose this is our 0 point, and I might have something like -1, -2, -3, 1, 2, 3. Okay, and I can go in and plot these things, okay? So for A, I have a point at -2 and -3, and so that would be a point here, A -3, A -2. Likewise for B, I've got a point at 1, so that would be something like this. And then for C, I have 2.5 and 2. Oh, sorry. What am I doing here? That's right, okay. C, 2.5 and 2. So that might look something like this. Okay? And so these are kind of roughly corresponding to the same points from the plot on the right. Okay? So this is an example of a residual plot that you can generate based off of any predicted line that you're doing relative to your actual points. And in fact, does a residual plot, is that constrained? So this thing that I drew over here, based off of these distances, is that constrained only to linear regressions? No, right? This could be any squiggly line of any kind, and I could still produce a residual plot. Okay. So as we build our intuition and familiarity with this, let's start to interpret some residual plots and think about why this tool is useful for us. Okay. So what I'm showing here is just like procedurally how you would go about generating a residual plot. So let's have a y hat here and a residuals plot here. Let's say this is our 0 point. Okay. And let's say my residuals look something like this. Who can tell me, or does anyone want to interpret this for me? It's not a rhetorical question. Someone interpret this for me. Anyone? Yes. Okay, so a lot of the points are clumped together. That's right. Do you notice anything particular about where the points are? Yeah.
Upper part of the graph over 0.
Yeah, so they're all above 0. Okay. So let me think for a second. What would that mean for like where this thing came from, right? So if you think about if you think about how we generate this, right? The points above 0 in our residual plot are above or below the line? Above the line, right? And if they're all above the line, then, you know, this type of thing, that would mean that this would come from a plot like this, right? So we go back to our original data. If our line looks like this, that would inherently mean all of the points are above the line, right? So from looking at the residual plot, I can actually make some inferences about like what my model is doing. And in fact, residual plots are a very powerful way of interpreting fits of your model. And so, okay, it's like, I look at this and you're like, okay, I can kind of understand why, you know, this thing would happen. And so therefore, you know, it's not actually a very good model, but like, if I could just look at the data, why wouldn't I just do this as opposed to this? What do you guys think? So, can you always do something like this? Yes.
Just a question. The straight line wouldn't be in the middle of the lengths. Because how can I view considering the minimum square or the minimum square?
Yeah.
How can we make that line over there? Since
Yeah. So put aside the fact that this fit doesn't really make sense. Okay. So this is more to build intuition about interpreting things with the residuals. You're saying, well, okay, this is not really possible in an OLS. But it might actually be in like a multi-dimensional thing. And if you're just looking at one X, it might look something like this. But also, maybe it looks, maybe there's something with like an X down here, okay? Maybe. And that might show up here in your residuals, like something like this. So it's not impossible for something like this to happen. And actually the first reason that I gave is more related to why you wouldn't necessarily always be able to see something like this, okay? So when you have an X and a Y, okay, great, I can plot it and I can visualize it, easy enough. Okay, but what about if I have an X1 and an X2? Okay, we haven't gotten to multivariate yet, but you can imagine, okay, I have 3 variables, I can visualize that in 3 dimensions, right? I can do X1 here, and then I can have another axes, right? It can be in 3D, and I can have X2. Okay, and then the cloud of points is in the 3D space. We can still kind of visualize how the fit relates to the points. Okay, so then how would you visualize that if I had X1, X2, and X3? Right, so you pretty quickly exhaust your ability to visualize like correlations between combinations of variables as soon as you're getting to some higher dimensions, or if you're trying to do regressions on like more and more columns of data, essentially. But I can always do this, right? It's just your Y against your residuals. And so You may not be able to see it directly from the data, but from the residuals, it is a very powerful tool that is an easy visual interpretation for whether or not you have something like bias in your model, like this, where everything is positive, and you're like, okay, that's an immediate signal that like maybe something is going on. Okay. And that is not the only one either. So I can also do something like this. So if I have a residual and a y hat, and this is my 0. So imagine my residuals look something like this. So instead of a spread of points, it's like this pattern. What would that mean for the original fit of data? So let's work that out, right? So let's say I have a 0 here. That means that x, y, let's suppose I have a straight line. The first 2 points are negative, big negative, little negative. Let's say the next one's 0. The next 4 are positive. So kind of big positive, really big positive, coming back down, and then negative. Okay. So you can even tell if the assumption of the functional form of your regression, so in this case, the fact that we assume that the fit is linear, that's going to pop out in your residual plot. Okay? Does this make sense? Does anyone have any questions about this? Okay, so then what are we looking for? So these are examples of bad residual plots. Okay? So what are we looking for in a good residual plot? What do you guys think? Or do you guys remember from your other regression classes? Yeah.
It would just be a random distribution of points.
Yeah, exactly. You would want, so if you think about it, the line that passes through the points in your data should be like randomly distributed around your line. If they are biased in one way, they will be biased in the residual plot, right? If they are, shaped in these ways like that, that's going to show up in the residual plot. So you want a residual plot that is randomly distributed and centered around 0. So your ideal residual plot will look like this. 0, okay, if I have something like that. I'm just going to throw out some points. Yeah, something like this, okay? And if it doesn't look like this, then be suspicious of your model. Yeah.
How come the ideal is not just all along 0 in like a line?
You mean, like, why not like this?
Yeah.
Yeah. That seems too good to be true. Well, okay. So let's think about that. In a linear fit, so if I had something like this, that would have to mean that what? My data is like exactly on the line.
Right, but there's like a spread vertically at which you would say it's not good for you, right?
Yeah, so Okay, I see what you're saying. So maybe not necessarily this blue one, but what about, like, wouldn't it be better to do something like this? So yeah, the tighter the tighter the points are around the 0 line does tell you something about the relative size of the error, right? But it doesn't necessarily mean that the model is bad. So let me explain. The thing that you are really watching out for in the residuals, so I'm doing a slight deviation from your question, but I'll get back to it. Ultimately, the thing that you're really looking for in your residuals is bias. Okay, is any patterns that are showing up in the residuals that differ from random centered around 0. That's like the real power of a residual plot. Yes, technically, the overall size of the errors does give some indication on how good the model is. And actually, it is a metric that we're actually going to talk about in just a moment. But just because the errors are tighter isn't an indication that a model is necessarily bad in and of itself. So imagine imagine something that has just random noise associated with it. So something that happens to have random noise and a trend. So actually, if we think about the example that I gave in our last time where I had 0.5 plus an error term, let's just suppose that I exploded the size of those errors a lot, right? And that's just like a random component of the data. But that our regression still accurately determines the slope to be 0.5, right? In that case, these residuals would be really big, but they would still be centered around 0. And so our conclusion that the coefficient was 0.5 is still like a good one, and that we would argue that that model is like an accurate representation of the true function that we were trying to measure, right? So larger residuals is like not necessarily a bad thing. It indicates our ability to predict something accurately, but if you just naturally have noise in there, that doesn't mean that the model is like behaving inappropriately. Yeah. Yes?
What if one side of the residual have a bigger value?
So, okay, so let's draw another example. So y hat resid, and let's say this is 0. Okay, what do you want me to draw?
Let's say the negative side,
Okay.
0, the scale of the negative value is greater than the positive. I mean the residue.
So, okay. So something like, so would you say it's still centered around 0?
Yeah.
Okay, great. So you're saying something like this.
But then in the negative side,
Yeah,
So
these are negative, right? So this is
Yeah.
like -1, -2. So our negative values are like -4, but our positive values that are around 1 or 2, something like that.
yeah, right.
Yeah. Yeah. So So what do you think? What is this telling you?
That was the question that I think, because one of my model showed that residue, so
Yeah.
I wasn't sure whether the bigness of the model.
Well, now I'm asking you.
Yeah, I
But on your
prefer-
thinking cap, think
I prefer to
critically.
be in balance, but if I see that, I would try to do other model. I'm not sure.
Well, okay, so let's hold off on let's say correcting it, but let's try and at least first interpret what's happening here correctly. Does anyone else want to give it a go? What do you guys think is happening here? Yeah.
Your model could be trying to fit outliers.
Yeah, exactly. And so residuals is a very easy way to observe outliers too. Okay, and so should we get rid of outliers? Okay, maybe, right? We're going to talk about outliers later on and what you should do with them. But this is an easy way of saying, hey, like my line is not necessarily biased. It's still centered around 0 generally. But it's getting dragged a little bit by outliers. That would be what I would interpret from this residual plot. Okay. Okay, great. Any other questions about residuals? Yeah, I don't know. A lot of this is like one of the easiest, simplest, most effective tools in data analysis, and yet I somehow feel that like people overlook this all the time. They just you just run a bunch of diagnostic tests and you don't create residuals. But something as simple as this would have helped us yesterday or on Monday with that Anscombe quartet. We could have looked at the residuals and been like, wait, there's like something really wonky going on here, right? So don't overlook this. Let me see here. Let's jump over to R and take a look at residuals. Okay. So let's get our same examples as before. Hang on one second. I don't know why my code looks really weird. Okay, that's fine. We'll improv it. Okay, so we're gonna do the same thing as before. We have our random uniform distribution for x. We're going to generate our error term, and then we're going to redefine x or y. So hopefully this will look pretty familiar for everybody. This is exactly the same code as last time. Okay, and we can even run And when I do that, and let me actually plot my x equals x, y equals y. So remember what that looks like, something like this. I think we're using slightly more data points this time. I think we only did like 20 or something last time, 50, don't remember. Now we're doing 100, and we are generating 100 points with x being, oh, this is different, sorry. So x is between 0 and 50, and our error is a normal distribution with mean 0, standard deviation 5. Similar to last time, but we're using slightly different parameters for our distributions, but it ends up creating a random set of points like this, and I can run a regression model, and we can see the results of that regression model here. Estimate of the intercept is 0.8, although very statistically insignificant. It's, a lot of the times, or 42% of the time, the intercept is going to be 0 or less, whereas for our slope coefficient, it's estimated to be at 0.4627, and so it's very statistically different from 0, and actually it's going to be a little bit less than 2 standard errors away from our, what we know to be the true value of the slope, which we know is to be 0.5. So, 1.5 standard deviations or something, 1.5 to 2 standard errors away. So, some percent of the time it'll actually be at that true slope that we can kind of estimate based off of the standard errors. Okay, and we also have our R squared at about 0.6. Okay, great. So I can actually add the fit line from my regression into here by leveraging a function called predict. So predict, what this takes in is the model object that I saved based off of the linear model. So that's example.model1. So if I use that, this will give a vector of 100 points generated here. Does anyone know what this vector of 100 points represents? Anyone guess?
Distance?
What was that?
Distance from the line?
Not quite. So that would actually be the residuals. And we'll actually show how to get that in a second. So predict, right? The thing that's getting predicted is y hat. So let's take a look really quick. So x is my vector of 100 randomly generated points. So x1 is 27.17582. That's just a random number that got drawn out of the hat. Okay? And let me save this as y hat. So y hat, the first value of y hat is 13.37988. Okay, so watch this. So, Okay, I'm gonna go up to my estimates. Point. I'll just do it like this, so I can keep track of this. Okay. So the model that I predicted has these two parameters, the intercept of 0.8051 and a slope of 0.4627. 8051 plus 0.4627 times times x, right? And so if I plug in my original x, 27.17582, I get 13.379. Okay. So what's happening out of this predict function? It is taking the x's and it is putting it back into the model that I had generated, and it's just re-predicting my y's, my y hat. And so in fact, if I draw a line here, it is finding this x value and it's saying, where on my fit line is that? That's what y hat is. And that's what the prediction gives for every x points in the data. Everyone okay with that? Any questions? Yes.
Can you explain that again?
Yeah. I can't draw this. Yeah. Okay. A ruler. No. So imagine there's a fit line here. Okay. And let's say this point right here is x1. You know, it's the first x randomly out of the 100 x's. Okay, so all the predict function is doing is it's saying at this x, whatever x is, like what does that x correspond to on the line? So for x1, the point would be like right here, that's y hat. Okay. And I can add that to the plot, and it would roughly make out that line, right? And so I could do something like this. Points, x equals x, and y equals y hat. And let's say color equals red. What do you think will happen? What do you guys think? It's just going to draw all of the corresponding red points for each of my x values. Okay? So that's the prediction. Questions? Okay. How do I calculate the residuals? Yes.
X minus y hat, or y hat minus x.
You're close, but not quite. Y minus x, so let's see, that would be, let's say this is 1 and this is,
Y minus y hat.
yes, there you go. So you want to do black dot minus the red dot, right? And that gives the distance. Yes. So I can do, I'm going to call this manual dot residuals is y minus y hat. Cool. And I can do this. and these are my residuals. Okay? You don't actually have to calculate them this way. There's a function called residual, or resid, which stands for residuals. And I can put in my model object. So that would be example.model1. And I can run this. And you'll see that the manual calculations and this are exactly the same. So if I look at the first 5 of the ones we just calculated manually, so 1 to 5, and I looked at the first 5 of the other one, they are exactly the same. Okay, so let me put that as a note. Exactly the same as what we calculated in manual dot residuals. Okay, so someone help me out here. How do I make my residual plot? What are the axes of the residual plot? Y hat. So x is y hat, and y is the residuals. Yeah, so manual dot residuals. Great, and boom. This is our residual plot. And here's 0. R will, when you do these plots in R, it will automatically take the range, which is kind of a nice way of like just being able to see, oh, is the 0 close to the middle? And if it is, then great, like it looks like our data is kind of centered around that. And do we see any patterns here? No. And so, yeah, in this case, it looks like our residuals are good. Okay? Any questions about this?
Is there something objective you can say about residuals? Like you've made some sort of model and you're trying to discuss its goodness.
Yeah.
Would you say, like, I looked at the residuals and I observed no pattern, or?
Yes, yeah, exactly. And this is a really great way of being able to say that you don't have bias in the model. In other words, that it is, that you aren't like systematically fitting wrong to your data. And that is extracted just from being able to look at it and say that it's essentially randomly distributed. It's a very easy, powerful way of saying that. And that's a test that, yeah, you can kind of get at with some numeric tests, but it's a little bit tricky. It's like context dependence. But this is a generalized tool that can be used for basically any model fit. Anything that we talk about in this class, where we're fitting some kind of line to data or something like that, you can do a residual plot. Yeah.
I want to go back to y hat.
Yes.
The prediction.
Yeah.
Is it exactly the same as the extension from regression, or are we generating new points in the regression line?
No, you are using the exact corresponding points that you put in as an input. Okay? You can put in new data if you want to predict differently. So, what do I mean by that? Let me go back to here. Okay, so the prediction tells you for this point, where is it on the line? For this x, where is it on the line? For this x, where is it on the line, right? But what if I want to know, okay, right here, there's no x's anywhere here. So x at 27, I want to know what is the prediction at exactly x equals 27. You can do that. We can do something like this. Predict example model 1, and we put in new data. And the new data technically has to be of the same form that we put in. So it's going to have a data frame with x equals 27. I think this will work. Let's see. Yeah. So predict is also a really powerful tool if you want to put in new data and see where in your model that would show up. Right? And like, in this case, it's a little silly because I could have taken 27 and I could have plugged it in. I could have said 0.8 plus 0.46 or whatever it was times 27, and then I would get the same answer to this. But you could have like a really big data thing that you wanted to predict. I calibrate my model to my x's and y's, and then I have a whole bunch of other data that I want to see how well it predicts on. And so this might be, let's say, let's say I have another 1,000 points here, and these ones are going from 50 to 100. Okay, and so there are no points, or let me just do 100. Okay, so this would allow me to like extrapolate my model fit out to points that are from 50 to 100 in like a separate data set. Okay. So predict function is a pretty powerful tool, and we're actually going to be leveraging that quite a lot when we think about doing validation for our models, which we'll get to, not today, but yeah, predict is going to end up being a pretty important function for us to use, so make sure that you guys have a good intuition of what it's doing. And if you have any questions about it, now's the time to ask. Great. Okay. Next up. All right. Oops. Okay. So this is actually getting to your question earlier about what about kind of the size of the errors. And that actually tends to be another kind of important metric to think about. And in that case, you don't have to look at the residual plots to look at the size of the errors, right? So the residual plot, again, mainly, not only, but mainly we're thinking about bias or systematic differences in our predicted versus the actual. The reason why you wouldn't necessarily look just at the residuals for the overall size of the errors is because they're kind of relative, and it can be hard to necessarily visualize the size of the errors by looking at a plot. We can like quantitatively just like add that up, right? So there's two kind of metrics that I'll talk about related to kind of the overall size of the error. And those are gonna be the residual standard error. So this is the standard deviation of residual values. So this is what is the spread of points about the regression line. Okay, and I'll give the equation just for reference, again, not something that we need to memorize or anything. The way this is calculated, the residual standard error is the square root of 1 divided by n minus 2 times the sum from y equals 1 to n of yi minus yi hat squared. And oftentimes we think about comparing this to the average value of y. So we take yi minus y hat, the distance between a point and our fit line, square that, right? Where you solve that, we sum it all up, and then we divide it by the number of points, and then we take the square root. This is a perfectly fine way of measuring kind of the aggregate error and the spread of the error, but it's not so commonly used in practice. Much more common is the mean squared error. And we're going to be using this a lot in this class. So this is the MSE. It's very similar. So instead of the spread, it thinks about the overall size, average size of the errors. So average of the square of errors. Okay, and the equation looks something like this. So I would, again, not expecting you to memorize this or anything, but you should be able to recognize this when you see it. It's pretty straightforward, based off of what we've done so far, right? We are taking our actual values minus the predicted values, right? So again, our points and the distance to our fit line, that's this. We square it, and then we just divide by the number of points. And so that will tell us the average distance each point is from the line. So if we think really kind of fundamentally about if you are using a model for prediction, and I'm thinking specifically about my ability to get as close as possible to the fit line, if I have, MSE of one model is equal to 10, and then the MSE of another model is equal to 20, and they're both fitting essentially the same data or the same y outcome, which model would be better? Model 1 with an MSE of 10 or model 2 with an MSE of 20? Which one? 1, right? So you want a smaller mean squared error. And so in model 2, our errors are twice as big on average, right? So they are twice as far from the fit line. So that tells us something about the relative predictive ability. So unlike an R squared, right? Where it's kind of a standardized number between 0 and 1, and an MSE is not indexed or standardized to anything. It's all relative to a particular type of outcome. And so you can't compare MSEs of like wildly different models that are using different data sets or anything. But if you are trying to look at a series of models that are estimating the same outcome, the same Y, then MSE is a really good tool to do that, right? And so if you have a model that's like, is Y a function of x1 and x2, or is Y a function of y2 and y3, right? I can compare those a lot more directly, in this case, by examining which one has a better fit, in other words, which one has a better sort of MSE, right? So again, this to me is an additional tool, one of my preferred tools, I would say, for thinking about specific properties of the model. The MSE will essentially help let me know how well I'm going to be predicting my Y values compared to actual values. It's not an end-all be-all, right? This doesn't tell you anything about model bias, and so you can have a really low MSE, but you can still have a lot of bias in your residuals. But I will say, last time we talked about, and I'll also mention, right, as you'll see in a second, that mean squared error is not limited to linear data. So if I have some data that looks like this, okay, and I draw a line like this. Remember, we were talking about this issue where maybe I have some line that maybe you might argue is overfitting, right? Or maybe really seriously overfitting, right? The mean squared error can actually be one of the tools to help us suss this out a little bit. And we're gonna talk about this a little bit more, but the concept here is, imagine I had some data points here from a data set, but I actually left some of the data out. And if I plug in that new data in here, and these points look something like this, I can now measure the distance from these new points to a variety of different points, right? So, or let me do, yeah, a better one. Okay, so like this one here, the black would go to there, the red one, the error is there, and the blue one, the error is really, really big, right? And so the MSE of the new points is going to be a really powerful indicator for how well my model is predicting for these new set of data points. And that's actually one of the tools that we're going to leverage to avoid and objectively say why the blue line and the red line might be worse than the black line. Okay, and so just think about when you have this, we're gonna call it a testing data set of the green points, how does that affect our MSE? Okay, any questions about this? Yeah,
I'm sorry, can you just explain this one more time?
yeah, sure. So last time I showed this kind of example where there are all these other fits that could go through all of the black points, right? And then we think about this as a classic example of overfitting. But for all of the for the purposes of the metric that we had come up with at the time, which is our model is determined, the model is determined by the size of the error, right? Then both the red and the blue are kind of better than the black because they have an error of 0 because they're literally passing through every single point. When we introduce this concept of leaving some data out and then calibrating the model to it again, that is the way that we can say that the blue fit and the red fit are like not necessarily good models, okay? And the objective measure of that, we are going to be doing that in this class using the mean squared error. Specifically what we're calling an out of sample mean squared error. But we're going to revisit that. Don't worry too much about that right now. But hopefully you guys can understand this concept that the MSE is a representation of the errors and the size, the distance between our actual model or our predicted model and the actual data points. That's kind of the takeaway for now for our MSEs. Okay, good. Any other questions? Okay, so let's jump back into R. And let's calculate the mean squared error. Okay. Who wants to help me out here? How do we calculate the MSE? I know I said you guys didn't have to memorize it, but did anyone write it down? Yes.
You take the sum of the y minus y hat,
Okay.
all x's,
Okay.
square that. Oh, you square
Square and
the
then you
difference,
sum.
sum that across the entire derivation.
Great. So MSE manual. Yeah, and yes, you guys can probably guess that there is a function that will do this for you, but let's make sure we all know how to do this and understand what's going on here. Okay, so y minus y hat. So y minus y hat, I can literally write that out like this. We are squaring this, and then we are summing it. Okay, and then we are dividing this thing by n. How do I calculate n? Anyone know? Length, yes, great. So the length of y, or the length of y hat, they're the same thing. Okay, please work. Yes, okay. MSE.manual, and we are hoping for one number here. 25.97142. Okay, great. Alright, how do I actually, is it, I don't think it's MSE. I can extract I thought I could extract the error. I don't remember off the top of my head, and my code is messed up in my notes for some reason, so don't worry about that. You can always look it up, but actually calculating the MSE manually is like very simple and straightforward, and so not hard to replicate this either way. Okay.
I'm sorry, right here when you entered names, example model 1, you're looking up the possible, I'm not even sure the term, but the possible functions that you can do with example model 1?
Yeah, so I guess I haven't talked about this. So example model 1 is like the model object that's stored. We ran the LM function and stored it here. And within this are a bunch of different things that you can actually extract out of that model. So actually we can look at that really quick. So coefficients, probably obvious, but if I do this, it will tell me the estimated or the predicted coefficient values, right, for the intercept and for x. Those are the same ones that appeared when I did summary. It can give you the residuals automatically, and so this will be those 100 residuals. So you see the last one, negative 0.43, 3.46, 1.37, 5.36. These are going to be the same as the manual residuals that we calculated. Negative 0.43, 3.46, 1.37, 5.36. Okay, what else is in there? Effects. What is effects? Let's find out. I don't use this that often. Gotta be honest, I have no idea what this is referring to. The most useful ones are gonna be coefficients, residuals, fitted values is a similar thing, so this is gonna be your predictions. We'll talk about some of this stuff later, actually. Yeah, those three are the ones that you need to know for now.
And I'm sorry to ask, but maybe, like, can you use names to look up any, maybe, like in this case, we have a linear regression model saved into example model 1.
Yep.
But if there's other, I'm
So
not
it
sure.
depends on the object type that names would make sense. So you couldn't use any object type that is storing things as a list of some kind that has assigned names, or actually even if it doesn't have assigned names, the names would just be the index number. You can do names, but otherwise, or like a data frame that has column names, you could do that. Otherwise, no. Like names is only on certain types of objects. Okay, any other questions? Yes?
What were the these that I posted on? Coefficients?
Coefficients, residuals, fitted values. Yep. And fitted values is the same thing as the predictions that we did earlier. Okay, what was I going to do here?
Looking up MSE.
Yeah, so, okay, I want to show an example of okay. Here's what we're gonna do. We're gonna create, a function. This is called bad model. So it's gonna take in a vector of x's, and it is going to return. So we're gonna do something like this: y hat dot bad. Do 0.75 times x plus 3, or no, plus 10. Okay, so let's suppose that you ran a regression model and you somehow screwed up, or you find some kind of model that someone made, but it turns out it's like a really poor fit to the data, or something like that. So we know that the true function, so this is still in reference to example 1. We know that the true function is 0.5 times x with an intercept of 0, but it does have some error, okay? So let's take a look at how our model metrics, how we might apply the model metrics that we talked about today against a bad model. Okay, so we've talked about residuals and the mean squared error. So let's do a comparison here. So let me run this guy. And so y hat bad is gonna be bad model inputting our x's. Okay, and so we have a new set of y hats. Great. So with residuals, we're trying to identify bias. And in the correct residual plot, which we saw before, and let me just, actually I'll just go ahead and pull that up so we can remember what that looks like. Here we go. Okay, right, this was our good residual plot, randomly distributed, centered around 0. Okay, what do you guys think the residual plot for the bad model looks like? Any guesses? We know that it's like systematically wrong, right? Because we know that 0.75x plus 10 is not the true model. We get to be omniscient and know the true model. So maybe try and visualize what you think might happen here. So plot x is equal to y hat dot bad, or yes, that's right. And then actually we need to do the residuals. We need to calculate the residuals bad dot bad, which is, how do I calculate residuals? Y minus y hat, exactly, so y minus y hat dot bad. Okay. Y is equal to residuals dot bad. Alright, visualize, and then is this what you thought it would look like? Okay, help me, somebody. Help me interpret this. What's going on here? Is this a good residual plot?
It's a very bad residual plot.
And why is it a bad residual plot?
Well, because there's a clear pattern, first of all, and it's mostly negative residuals.
Yeah.
Those two things.
Yeah, here's our 0. Are we centered around 0? No. it's all below 0. And not only is it not randomly, it's like sloped down, right? Bad. Okay. And in fact, I can even, let's do this. So as I was describing, one of the really powerful pieces, or one of the really powerful aspects of the residual plot is because I can apply this even across many, many dimensions. In this example, it's only 2 dimensions, so we are actually able to visualize the fit manually. And so that could be a double check to confirm that there's something going on in the residuals, and thus the model is acting kind of weird. So I can do something like this: f equals x, y equals y. I so rarely use the base plots. Does anyone know, is an AB line, is A the slope or the intercept? Anyone? Does anyone? Okay, well, we're just gonna guess and find out. I'm gonna guess A is the slope. So here's our data, and then here is our best fit line. No, sorry. 10, and this is 7. I got it backwards. Okay, yeah, there you go. So this is the bad model, and relative to all of the data points. And so that was what our residual looked like. It was like a little wild. Okay, mean squared error. What is the mean squared error? Remind me, someone. Sorry, I heard something. How do I calculate it? Yes, y minus y hat, bad in this case. Square it, yep. And sum it and then divide by length of y. Okay, so our MSE.manual, so remember I said that MSEs aren't really comparable unless you are working with the same outcome variable. You're working in kind of the similar modeling space. You want to see which model better predicts a particular type of outcome. And so in this case, we can compare the MSEs. So our mean squared error for the one that we calculated originally for the actual linear regression model is 25.97. And do we want a bigger or smaller mean squared error? Smaller, great. So then MSE dot bad, please be bigger. Yes, it's way bigger, it's 308, okay? So the average error of our linear regression model is 26. The average error of this random bad model that we generated is 308. I just totally lost my train of thought. So with the mean squared error, again, the magnitude of this is context dependent. There isn't something that we're indexed to compare whether it makes it good or not, but I can relatively say that this model will have smaller errors and better prediction outcomes relative to this other model. Okay. Questions about mean squared error? Okay. So one last metric we're gonna talk about today. It's a good one to know, but it's not necessarily one that I'm like commonly pulling out of my toolbox to look at, to be honest. But we've been, let me just pull it up again. We've been looking at the summary output for our model, and we've walked through most of the stuff, right? So actually the summary outputs tells us, now we should be able to understand this portion of the summary statistics of our model. What do you guys think this means? You look like you want to say something. No?
Minimum residual value?
Sure. So, sorry, yeah?
Minimum residual.
Yeah, this is the smallest residual, largest residual. It's telling me something about the distribution of the residuals. Right, and so if the median is like really different from 0, go check your residual. Actually, check your residuals anyways, but double check your residuals, right? And then, you know, is the spread of them relatively similar, right? So this is the first quartile, third quartile, so they should be kind of symmetrical around 0, and we kind of see that relatively. So this is like the lazy man's version of looking at the residuals, but actually go in and look at them, okay? Don't just look at this. Okay, we talked about coefficients, standard errors, statistical significance last time. Now we know what the residual standard error is, right? The RSE, this is analogous in many ways to the mean squared error, but I use this a lot less commonly, but now we know residual squared error. R squared, we talked about that last time. Adjusted R squared, we're not going to talk about this for another couple weeks, but we will get there. Last one, F statistic. Okay, what is the F statistic? So this is the last thing that we're going to talk about today. Okay, back to the iPad. I want to put in black. Statistic. So this is similar to the standard error. So the hypothesis that all betas are equal to 0. I'm going to write the equation just for reference. F is equal to the sum I equals 1 to k and I y I. So the average divided by k minus 1. It's a long and boring formula that I have never once manually computed outside of a class, and I'm not going to make you do that either. But this or is oftentimes relevant for model selection. Okay, so this is the equation. The actual thing that an F statistic is referring to is essentially the way that you think of an F statistic is almost exactly the same interpretation that we have for coefficients and standard errors. It is saying, so if the analogy would be something like this. The coefficient of our model, if it is statistically significant, it is indicating that there is some kind of non-zero effect of this variable on the outcome, this individual variable on the outcome. And so if we were thinking about tests of significance in terms of like a statistical hypothesis, it would say, oh, I'm testing whether or not this particular variable has an effect in the model, right? And if you are at a certain level, then you're saying, oh yes, then my hypothesis, would be proven true or false, depending on that statistical level, that this variable is doing something. The F-stat is the exact same interpretation, but instead of just looking at one variable, it's saying all of the variables compared to no variables. So the idea is overall, is it like worth including the variables to kind of have some kind of fit to the model versus what do you guys think would be kind of the counterfactual or the like default thing that you would be assuming? Think about it. Well, what would I be comparing to if I had no x's? It would just be the average value of y. Does the average value of y explain y better than including these variables in the model? Okay? And the F-stat is telling you that the hypothesis is like which one's better, taking all the x's out or having them in, and if there's statistical significance here, then that means adding all the variables in is better than not having them at all. Okay? So, same interpretation as everything here. And actually, I can show you guys one thing to kind of drive that point home. So there is a way that I can manually force the model to not have an intercept. I think it's -1, right? Does anyone know off the top of their heads? Data is for model.1. I think that's right. Okay, summary, example model 2. Oops. Yeah, great. Okay, so adding a -1 there basically tells the model don't set an intercept, assume the intercept is 0. So when we forced it to do that, we get this. And importantly, your F-stat and this, the the statistical significance is not actually showing like the t-value conversion thing, but these two standard error significance tests end up being exactly the same, right? And that is because, like I was saying, the f-stat is testing whether all the things in the model versus none of the things in the model. If there's only one thing, if there's only one variable in the model, then this significance test is the same hypothesis as your f-stat, and you get the same values between your f-stat and your standard error test of significance. Okay? Questions?
Quick question on this one.
Yes.
So just reading through what it says under behind F statistic, we've gone from 739.1 on 1 and 99 data.
Yeah.
It had been between 1 and 98 data. What is that portion of it?
DF refers to degrees of freedom. So what is a degree of freedom? So this is a good little aside that we're gonna have, or to be having. So if I have one data point, or let's say I have two data points like this. The degrees of freedom is in reference to the number of explanatory variables relative to the number of data points that I have in my data set. And when you have, so conceptually the way to think about this is, let's say that I have 10 different variables, but only like 2 data points, then I have too many things that could be explaining the variation in the data, right? When I have a one-to-one matching, you have no wiggle room for your fit, essentially. And so you have, so in the first example where you have too many, you actually can't compute the fit. When you have exactly the same number of explanatory variables versus number of data points, then you have no wiggle room in the way that you fit a point that's going through your lines. So the degrees of freedom is kind of like the relative amount of wiggle room that I have in the data points compared to how many variables I have to explain that variation. And so the way that we calculate degrees of freedom, so this is df. So this is equal to, so it's often computed with slight modifications for some specific statistical properties, but usually you are talking about doing something like n minus k, where this is number of data points, and this is number of variables. Okay? Number of explanatory variables. So sometimes you'll see n minus k, sometimes you'll see n minus k minus 1, sometimes you'll see n minus k minus 2, there are kind of nuanced statistical reasons for why we would do something like that. But yeah, this is like essentially wiggle room, describing fits and the data. And so going back to here, wait. That was in there, right? One sec. Yeah, so this shows up here, n minus k. So it is part of the way an F statistic is calculated, and sometimes you kind of want to see that explicitly, and so in the summary call, it is pulled out. And here we are 99 degrees of freedom because there are 100 data points and we have one explanatory variable, so it's 100 minus 1. In the other one, we have 98 degrees of freedom because it is 100 minus 2 explanatory variables, or 2 parameters, your slope associated with your x and then the intercept. Okay. Yeah, does that answer? Okay, great. Yeah, so now we are, I think, truly able to interpret the full thing, except for the adjusted R squared. Don't worry about that, we'll get there. Yeah. Any other questions? Yes?
Could you go back to the formula for a statistic?
Absolutely. Connect. Oh yeah, you just wanted to see it. Okay. Sorry, I'll leave it up. Sometimes I move too quickly. But you can also look this up, and you also don't have to memorize this. But good for reference in your notes, so you kind of understand where this is coming from. You know, like in this class again, we're not a theory-based class, so I'm not going to get into how you derive this and yada yada. But okay, I'm not sure how useful this is, but hopefully you can see some of the elements that I was talking about as they relate to the F stat, right? Like our counterfactual being just the average value and how that would compare, right? That does show up in the equation here. So you're doing aspects of, in the numerator, this comparison against the average versus like model outcomes, and then we also think about, right, the degrees of freedom playing a role in influencing how the F stat looks. And actually that is a qualitative thing to think about, and this relates to the standard error as well. So if you look back in your notes, the standard error is has a term. I'm just double checking to make sure. Right, so the standard error has a term that's kind of like this, where you have a divided by n minus 2. That is related to the degrees of freedom too, but conceptually, one of the things to think about is what happens in the model when I add more data, more and more and more data. What do you think happens think about this qualitatively, if I have more data to calibrate my model on, what does that mean for my estimates, and how good those estimates are? What do you guys think? Does it make my estimates more certain or less certain, calibrating on more data? More certain. And that means that my confidence about what the average slope of my x is like better, right? As I add more and more data. And that is reflected in these metrics, right? So think about in the standard error, you are dividing by an n, right? And so as my n goes up, my standard error gets smaller. Same thing here, right? I am dividing by an n, and as a result, as you add more and more and more data into the model, your F statistic gets your F stat gets smaller, which I know we didn't talk about how that converts into the actual significance test, but it makes the probability smaller. And so in the same way, like the standard error will be shrinking. And so our intuition is kind of backed up by the actual quantitative calculations. And so that's why I think, even though I'm not necessarily asking you guys to memorize this in any way, it is still kind of useful to have good intuition about what these values kind of stand for and what they're actually doing, and how they change as like the model changes or the data changes. You wanna be able to get the intuition to look at some of these values and be able to say, oh, okay, that makes sense, or oh, like maybe something looks wrong, okay? And so that's what we're trying to do in this class. We're really gonna think about the application of these values like this, and less so about like how you prove this and how you like get to this equation, okay? All right, any other questions? Okay, that's it for today. Thanks everyone. Office hours, my office hours are tomorrow morning, so swing by if you need.